everyone, I'm Venkatesh. Welcome to our EUSIPCO' 2021 presentation on deep learning based non-invasive diabetes predictor using photoplethysmography signals. I just graduated from Purdue University with a master's in electrical and computer engineering. This is my internship work in analog devices that was pursued between May 2020 and December 2020. I worked with the digital healthcare team under the guidance of Foroozan, the co-author of this publication. I was constantly guided by a group of extremely proficient individuals in the field of signal processing and deep learning who were very supportive and helpful in clarifying most of the questions that I had in the pursuit of the project. Before stepping into the details of this publication, at this moment, I'd like to convey my heartfelt thanks to everyone in analog devices. Let's begin the presentation with the motive behind our project. Diabetes is a chronic health condition that is characterized by increasing blood glucose levels, causing severe health hazards. It is reported by the World Health Organization that over 422 million people across the globe suffer from diabetes. In addition, World Health Organization also reports that the number of deaths caused by diabetes amount to 1.6 million. Currently, doctors utilize oral glucose tolerance test, fasting plasma glucose test, postprandial plasma glucose test, random blood sugar test, and HbA1c test, also known as hemoglobin A1c test, to diagnose diabetes in laboratories. But they are invasive, expensive, and time consuming. Hence, a continuous non-invasive screening tool that can diagnose diabetes accurately in quick time can be extremely helpful, especially in places that are deprived of medical care. This can also help in the early detection of diabetes before being sent for the confirmatory diabetes testing using HbA1c. Now, before stepping into the specifics of this project, I feel it is important to get a basic introduction into the world of photoplethysmography. Photoplethysmography is a non-invasive medium which uses optical technique to measure the volumetric variations of blood circulations. Light from the LED falls on the fingers or the wrist and is backscattered or transmitted to the photodiode, which measures the amount of light detected in the form of a pulse wave. While the photodiode is placed in the opposite side of the LED in the transmissive PPG sensor, it is placed adjacent to the LED in the reflective mode. You could have a look at the images present in the middle of this slide. PPG signals are composed of pulsatile and non-pulsatile components, also known as AC and DC components respectively. The AC component consists of systolic and diastolic phases separated by a dichrotic notch. While the AC component is synchronized with the heart and related to arterial pulsation, the DC component is related to light absorption in the tissue, vein, and static blood. Talking about what this work sets out to accomplish, the primary goal of this work is to distinguish between diabetic and non-diabetic patients using PPG signals, which are used to analyze vascular diseases. Nirala's paper proposes a support vector machine-based screening tool to detect diabetes using 37 features collected from TOE PPG. Deep learning paves the way for automatic feature selection, where the extracted PPG features in time or frequency domain make the existing approaches sensitive only to those features from the physiology point of view and signal processing point of view. Roberts' paper proposed a deep learning technique using PPG signals that could serve as a potential biomarker for diabetes detection. We use PhysioNet's Mimic3, also known as Medical Information Mart for Intensive Care database, to predict diabetes using PPG waveforms, which are transmissive PPG signals collected from fingertip with a frequency of 125 Hz. In our knowledge, this is the first work that is done over this dataset that was released in April 2020. In addition, most of the existing works are performed over the datasets collected by the authors themselves, which we can't access. This kind of an analysis over a public dataset helps the researchers in the long run to significantly improve the results and design state-of-the-art algorithms to provide cutting-edge results. We experiment this dataset by running them over custom variants of existing deep learning architectures and classify the patients into healthy and diabetic patients where the pre-processed PPG signals are input into the architectures. You could have a look at the tabulation of the statistics over here. We have a total of 808 patients that were randomly selected from the MIMIC dataset that contains more than 10,000 patients. There are 584 patients put in training and 224 patients put in testing. Out of 808 patients, 341 are diabetic, of which 290 people have hypertension as well, in addition to diabetes. we have an equal split of male and female diabetic patients. Please have a look at these images. The first two images represent the PPG waveforms of diabetic patients, and the last two images represent that of the non-diabetic patients. Each signals are 10 seconds long over here. It was mentioned in the work of Nirala that an absence of dichrotic notch can be observed in the PPG signals of diabetic patients. But on exhaustive analysis of the mimic3 dataset, we observed that the absence of dichrotic notch did not turn out to be a definitive feature for diabetes. On pursuing further research, it was found that the absence of dichrotic notch can be attributed to various other factors such as aging, cardiovascular diseases, etc. Due to such complications in identifying the diabetic and non-diabetic patients just through the naked eye view of PPG plots, we decided to make use of a deep learning algorithm that could automatically take the intricate features that could possibly differentiate between the two classes. The ultra-low frequency signals are introduced due to respiration, which basically causes an effect known as baseline wandering. A high-pass Butterworth filter of 0.5 Hz is implemented to remove the baseline wandering caused by motion, impedance of the sensor, and respiration. In addition, a 10 Hz low-pass filter is implemented to retrieve the PPG frequency band of 0.5 Hz to 10 Hz. We segment the long PPG data of a patient into several segments of 30 seconds each and represent the same by means of a 2D scaleogram. Technically, scaleogram is the absolute value of continuous wavelength transform of the signal that is plotted as a function of time and frequency. Scalograms can identify the low frequency and fast changing frequency components of the signal. It preserves the time and frequency localization parameters of non-stationary signals and is better compared to short time Fourier transform. In order to differentiate the important features in PPG from motion-induced noise, we need to reject the corrupted segments from motion artifacts, for which we designed a simple signal quality check algorithm using template matching. We reconstruct the PPG signal using the peaks extracted and perform least square based linear regression of the reconstructed template signal with the original signal to check for correlation. The segments with correlation coefficient greater than 0.8 are considered to be uncorrupted signals that can be passed into our deep learning model. Signals which don't follow morphology, like say a notch on the anacrotic phase of the PPG cycle, contrary to the usual catacrotic phase in a mimic3 dataset, are neglected from the dataset itself. As you can see in the block diagram, each 640 cross 480 cross 3 scaleogram is normalized and resized into 320 cross 240 cross 3 before feeding into the CNN so as to perform computations faster by preserving the aspect ratio. The resized image was sent into a slightly modified VGGNet architecture. The CNN is basically like a feature extractor over here. As shown in the figure, the primary model possesses 9 convolutional layers, 3 pooling layers, and 1 global average pooling layer. The same kernel size of 3 cross 3 was used for all the convolutional layers. The first two convolutions are done successively in the following way, where 64 3 cross 3 filters are passed on to the input feed. Pooling is also done for this layer. We repeat the same using two convolutions of 128 and 256 3 cross 3 filters, followed by 3 convolutions of 512 3 cross 3 filters, and then pool the convolved feed using global average pooling to obtain a one-dimensional arrangement of neurons. We pass this through a fully connected network containing 2 dense layers and finally to a classifier which has 2 neurons, where each one represents a class, diabetic and non-diabetic. In addition to the PPG input, we add additional fully connected network modules with 3 dense layers for other inputs such as age, gender, hypertension classification, and heart rate. We concatenate the additional models along with the primary PPG model before passing it through the softmax classifier that can be used to classify non-diabetic and diabetic patients. We use a batch size of 8 running for 20 epochs set at a learning rate of 0.001 using Adam optimizer and used softmax classifier in the final layer of fully connected network to train different models with the above mentioned set of parameters as inputs. We made use of Tesla K80 GPU for this purpose. Out of several CNN architectures that were tried, VGGNet gave better results for the dataset that we used. This test was carried out with different set of inputs. Kindly have a look at the table at the bottom of the slide. 4 different models were built using different sets of inputs such as PPG, PPG plus hypertension classification, PPG plus hypertension classification plus age plus gender, PPG plus hypertension classification plus age plus gender plus heart rate. We see that the combination of PPG signals in addition to the age, gender, and hypertension classification parameter gives us the best results. It can also be seen from the tabulation that the performance degrades on the addition of heart rate to the best performing model. This indicates that the model gets confused on the addition of heart rate. It can be keenly understood from the table that the model with hypertension classification as an additional input along with the PPG signals perform relatively better than the model built only using PPG signals. The confusion matrix provides us a better understanding of true and false predictions of diabetic and non-diabetic patients against the ground truth. In order to understand the diagnostic capability of the classification models at different thresholds to predict diabetes, we make use of receiver operating characteristic curve. Area under the ROC curve gives an aggregate measure of performance across different classification thresholds. The ROC curve depicts that the input combination of PPG signals with age, gender, and hypertension classification achieved the best performance with an AUC value of 0.83. From the tabulation, we can observe that the sensitivity for our best model is 76.66%, specificity is 76.11%, and accuracy is 76.34%. The results are comparable to the gold standard shown in the tabulation for diabetes monitoring and the few existing research works that are present in this area performing better in a few study parameters. As I had already mentioned while showing you the plots of PPG signals, Nirala's publication proposes that absence of dichrotic notch can be observed in PPG signals of diabetic patients. We show that it is not a necessity to have this feature for all diabetic patients, owing to several other factors such as aging, cardiovascular disease, etc. This is one of the main reasons as to why conventional handcrafted machine learning techniques would not turn out to be very effective. Deep learning can be very instrumental in such situations. This technique can be used by doctors as a screening test for diabetes before proceeding with the medical checkup. This can further be improved by increasing the training dataset size by adding more data from the Mimic3 dataset, which could boost the performance of our model to reach FPG test level. We could further improve the model by testing it over our in-house PPG dataset with appropriate clinical ground truths. In addition, the morphology of PPG signals are hampered by means of baseline wandering, as we literally kill very low frequency signals below 0.5 Hz. We intend to pursue research in our future work. Also, in our future work, we intend to design the neural network architecture to automatically pre-process the PPG signals without the need of manual filtering. Once again, we thank EUSIPCO 2021 for the opportunity. And as a closing note, we request everyone to stay safe and follow necessary precautions to combat this pandemic. We are in this together. Thank you.